Hello, I'm Vanessa Tan, and I will be presenting our paper entitled MATA, Mission Attitude and Telemetry Analysis Software for Microsatellites, on behalf of my colleagues John Loy Labrador and Mark Cesar Dalampas. With the rise in popularity of small satellites, there has been an increasing demand for a software tool that covers different stages of satellite development, from ideation, testing, and up to post-launch assessment. Most commercial software provides full space environment simulations, like orbit projection, magnetic field, gravitational force, and many more. However, centralized software that can be used for different stages of satellite development are either time-consuming to develop or are prohibitively expensive. This work presents MATA, a simulation and visualization software originally developed for Philippine Diwata microsatellites, but is capable of being modified to cater to other small satellite development requirements. The rest of this presentation is divided into 3 parts: the different operation modes of MATA, its main features, MATA software framework, and other applications made from the said framework. Before we dive into the different operation modes of MATA, I'll first discuss 2 important terms in satellite simulation systems. First is a two-line element set. This TLE is a data format describing the orbital elements of satellites for a given point in time. This is used in the calculation of the orbital position of the satellites. Next is the telemetry. Satellite telemetry is the recording and transmission of data from the satellite to the ground station. One of the main challenges in using telemetry is how to interpret the data and give significant insights to end users. Hence, the creation of our simulation software, MATA. Now, I will be discussing how MATA's operation modes can be used in the development of small Earth observation satellites. Satellite engineers need to first plan the orbital path of the satellite and test its pointing capability. With MATA's Quick Simulate mode, users could create different scenarios based on the following parameters: the two-line element set, initial date and time, temporal step size, reaction wheel control gains, and target attitude values. MATA uses mathematical models to simulate the attitude control scenario and utilizes the simplified General Perturbation version 4 or SGP4 model to determine the orbital position. After simulating different scenarios, the engineers would then test the behavior of the satellite with a hardware prototype, which is usually an engineering model similar to the one currently in orbit. In this hardware-in-the-loop mode, MATA has 2 components: the main MATA visualization and an extension named MATA Hardware Interface, or MATA-HI. MATA-HI converts the initial parameters and sends them to the onboarding computing units as universal asynchronous receiver-transmitter signals. The S4 system, or the Small Satellite Simulation System, would then try to mimic the attitude of the satellite given different parameters. The last operation mode is the telemetry replay mode, which is helpful for ground station managers. After sending the satellite commands, ground station managers download the historical data or telemetry of Diwata satellites. This mode then enables them to visualize what happened in orbit and in turn better understand the telemetry data. We now move on to the features of the MATA simulator. There are 6 features: orbit visualization and attitude visualization, celestial body modeling, optical payload views, intuitive user interface, and telemetry status display. I will be only discussing the 3 important features, and the rest could be seen in our paper. First is the visualization of the satellite orbit in 2D and 3D. In this example, the orange line here is the orbital path of the satellite. Using the SGP4 model, MATA projects the satellite's position in the 3D environment based on the Earth-centered inertial or ECI coordinates. Furthermore, it performs coordinate frame conversion from ECI to Geodetic, enabling the projection of the satellite position on a 2D map. This feature is useful for determining satellite line of sight with respect to a target on the ground. Next is a visualization of satellite attitude. In the case of Diwata satellites, 3 attitude control modes are typically used, namely nadir, off-nadir, and inertial pointing modes. An application of this feature would be in the verification of external noise in an observation procedure that was not performed correctly. By using MATA Quick Simulate mode, a future observation could be planned to avoid similar mistakes. This feature can also be used for testing other attitude control systems, like PID controllers and reinforcement learning algorithms. Lastly, an important feature of MATA is the capability to project what optical payload sees based on the telemetry status and the 3D environment. MATA projects the views of Diwata's optical payloads, namely Wide Field Camera, WFC, Space-Borne Multispectral Imager, SMI, and Middle Field Camera, MFC. The WFC is a panchromatic fisheye camera, while the SMI is a multispectral imager with a liquid crystal tunable filter. Moreover, MFC is also a panchromatic camera which focuses on aiding in the attitude control calibration and geolocating images taken by the other payloads. The HPT, or High Precision Telescope, which has red, green, blue, and near-infrared bands, could also be introduced in the simulator, but the simulator is currently limited by the low resolution of the Earth model. The accuracy of this feature was verified through comparison of projected views and captured images with telemetry recording as shown in this example. We now move to the last part of the presentation, MATA's software framework. There are 2 major components of the framework, the managers and the controllers. The 4 managers handle the communication between the different controllers. These managers use the singleton pattern to make sure that they only have one instance in the system and would coordinate with other classes in the framework. Meanwhile, the 5 controllers handle the methods and computation for particular components of the simulator, such as the satellite and celestial movements, socket connections, attitude computations, and the user interface. With the modularity of the framework, we could easily integrate other controllers and make new applications like this reaction wheel visualization, which serves as an educational tool to help students generate plots and create scenarios of the reaction wheels. Another application that we did using MATA's framework was the push broom scanner. This application allows the user to capture images using the push broom imaging method. Here is a sample method or sample output of the push broom scanner using the MATA simulator. To summarize, the main contributions of this paper are the following: development of a simulator using historical data or telemetry data from Diwata satellites for creating user-defined scenarios, development of a hardware-in-the-loop system with MATA for system evaluation, creation of a 3D environment that can recreate attitude and imaging payload views from recorded satellite telemetry, and lastly, the development of a modular and flexible framework for additional applications such as mixed reality satellite training and space educational software. For future work, the team would extend the simulator to developing a small satellite simulation system, which can test the satellite's power distribution system, command and data handling, ground control system evaluation, and even cloud and star tracking simulations. Please check out our paper for further discussion about our work, and visit the Stamina for Space website to learn more about the current satellite developments in the Philippines. Please don't hesitate to reach out to our team for any questions or comments. Thank you for listening.